Okay, it's really my sincere pleasure to introduce Mark Anastasio from the University of Illinois Urbana-Champaign. I'll keep my introduction short. I think he's got some great things to tell us about how to do machine learning in a rigorous fashion, and maybe some of the things we can try to avoid. With that, thanks so much.
Okay, thank you, Webb, for the introduction and for the invitation to be here. It's my pleasure. Just a bit of background. So I am also an image reconstruction method developer, like many of you, and we also use deep learning for a variety of purposes whenever we think it makes sense, like many of you. But today I'm not going to be talking about any new reconstruction methods or any new machine learning methods. I'm going to be talking about something that's just important, and that's how we should think about assessing some of these new machine learning technologies, specifically for medical imaging applications. So I'm going to start off with just a little bit of background to get everybody in the mood. And then I have a couple case studies I'm going to walk through. One has to do with image denoising and how we, some surprising behavior that you might see or might not see. Then I'm going to talk about deep generative models and give you some insights into how we might want to think about assessing those. And if there's time, I'm going to throw out some new definitions about image hallucinations at the end of my talk. Okay. So many of you know that in the field of medical imaging, objective measures of image quality have been widely advocated. Right? So objective measures or task-based measures of image quality reflect the utility of an image for a given task. And these are different from the traditional physical metrics such as MSE, signal to noise ratio, SSIM, in the sense that, again, these measures reflect how useful an image is for a specific task. That's important for us as medical imaging scientists because we know that medical images are often acquired for specific purposes. So the way that we need to think about image quality is very different than how someone in computer vision, for example, thinks about image quality. Okay. And some of the canonical tasks that are relevant to us, of course, are signal detection and parameter estimation. Okay. So human readers are often the gold standard, well, at least if a human is going to be the entity reading the image at the end of the day. But we know that when we're developing technologies, it's not convenient or feasible to do reader studies with professional radiologists. So numerical observers are often used as a surrogate, right? Numerical observers can be used to make a decision and based on the decisions they make, compute objective measures of image quality. Okay? And for signal detection tasks, there's a couple different types of numerical observers that you may be aware of. Some are anthropomorphic numerical observers. So if we want our numerical observer to sort of mimic or behave like a human would do. And then there's numerical observers that approximate the Bayesian ideal observer. And I'll talk about that in a moment. And deep learning is enabling both types of these observers. And although I'm not going to be talking about today, but I wanted to let you know. Okay. So let me talk a little bit about the ideal observer, because I'm actually going to be using this in my first case study. Okay. In the field of medical imaging, for the past 20, 25 years, the ideal observer has been advocated for optimizing imaging hardware and data acquisition designs. Okay. So the ideal Bayesian observer is a numerical observer or a model observer that achieves the best theoretical performance on signal detection tasks, for example. Okay. And the ideal observer employs complete knowledge of the object and noise statistics. And again, if we use an ideal observer to compute objective measures of image quality, then when we optimize an imaging system, we can ensure that the task-specific information is maximized in our measurements. That's kind of the logic behind why, as an imaging scientist, we should care about ideal observers. Unfortunately, the ideal observer is generally very difficult to compute. It uses the likelihood ratio to form the test statistic. It's very nonlinear in general. MCMC methods are sometimes applicable, but they're also limited and challenging to implement. Fortunately, deep learning can come to the rescue here. And deep learning is a convenient tool, specifically CNNs, for approximating the ideal observer for signal detection tasks. Okay? They can be widely applicable. You can consider background variability, different noise sources. It's a very, very general framework. And just to let you know, the past few years, my lab has written a series of papers where we investigate CNNs or hybrid CNN sampling approaches for approximating the ideal observer for different diagnostic tasks, either binary signal detection, N-class classification, or detection estimation tests. Okay, so that's the background. So let me get on to the first topic I wanted to talk about, and this is a short case study that has to do with some behavior that may occur when you look at deep learning based image denoising. So I think most of you know that denoising is one of the applications of deep learning that's getting traction. It's very, very relevant to medical imaging applications. You already heard about it a few times today. And I'm going to be considering just a vanilla CNN based denoising operation, where we have an input image, which is our noisy image. It's fed through a series of convolutional layers and followed by nonlinearities. We stack these guys, and then the output is the estimate of the denoised image. And I'm also going to be considering that a traditional MSE loss function was used to train this network. But you could use a perceptual loss, you could use whatever you lost. But in this simple study, I'm just going to assume an MSE loss function was used to train this network. Okay. So what I really want to look at is what does this CNN-based denoising operation do to task-based performance? So important questions are, does this denoising operation always improve signal detection performance, or and if not, when does it? Okay. So in the first study, I'm going to consider a computer simulation setup where I consider a lumpy background object, which is shown here. I just consider a very simple Gaussian signal blob, and then we add noise. So we take the signal, insert it into the background, the lumpy background, we add noise, and we get this realization here. So this is going to be the input to the denoising network, and the output is going to be an estimate of the clean background or the background plus signal. So we'll assume the signal is inserted into half of these backgrounds and not in the other half. Okay. And what we looked at was we wanted to understand how does the depth of the network affect the signal detection performance on the denoised images. Okay, so we computed, in this case, both physical and task-based image quality measures on the original noisy data and then also on the denoised image data. And again, we wanted to understand what the denoising operation did to task performance. Okay. And here are the numerical observers we used to compute our objective image quality measures. We considered three. One was the ideal observer, which I briefly told you about. So this is the upper bound in detection performance. Then we implemented a Hotelling observer, which is the optimal linear observer that uses the second order statistics, the covariance matrix of the image data to form its decision. And then just a simple naive match filter. Okay. So here's the first result. And this shows a plot of the singular values of the covariance matrix of the denoised images. Okay, so we have singular values. This is the index of the singular values. The first curve on the top here, the solid red curve, this is actually the singular spectra corresponding to the original noisy images. This band of spectra here correspond to the denoised images. And when you go down, when you go from blue to red to yellow to purple, this corresponds to denoising networks of increasingly larger depths. So what this is showing, well, as soon as you apply the denoising operation, the covariance matrix becomes more, I would say it becomes worse conditioned. And as the network depth gets higher, the conditioning gets even worse, right? And this doesn't always happen. This is just what happened in this particular case, of course, okay? And then based on that, here are the results of the image quality assessments. Let me start at the bottom here, and these reflect the traditional measures. I'm going to show the SSIM and the root mean square error. In this first column here, these are the values corresponding to the original noisy images. So if we look at SSIM, originally it was very low on the noisy image. And then as we look at the output of the denoising network for different depths, we can see that the SSIM increases. So it's basically as the denoising network gets deeper, the SSIM value gets better, right? That's kind of conventional knowledge. That's what computer vision scientists want to happen, right? Similar story with the RMSE. It started off high, but then when we apply the denoising network, it gets smaller. And the RMSE gets smaller as the depth of the denoising network gets deeper. Again, deeper, better, everything's good here. Let's look now up here. These are the task-based measures based on signal detection performance. I have the AUC here plotted against the number of convolutional layers in the denoising network, okay? And the three colors correspond to the three observers. The red is the ideal observer, the green is the Hotelling, the purple is just the simple matched filter. In each case, the dashed line corresponds to the AUC value on the original noisy images, okay? And what we see here is that in all of the cases, the AUC decreases as the depth of the denoising network increases. So if we look at the ideal observer, the performance goes down similarly very strongly with the hoteling. With the non-pre-Whitening match filter, it doesn't really go down that much, and probably because it's not using any of the higher order statistics in that case, so it doesn't care what the denoising network did. Okay, but the take-home point here was that in this particular study, when we increased depth, the traditional measures of image quality went up, the task-based measures went down. Okay, I'm not saying this always happens. I can tell you it does not always happen. What I'm telling you is that it can happen, and therefore, when we assess these technologies, we can't stop with the traditional measures, right? If we're going to claim that this is useful for medical imaging, then we need to do something to show that the actual objective measures are improved by use of the network. Okay, so just a summary of the and I probably already said this, but a summary of these observations: the deep learning-based denoising operation degraded the conditioning of the covariance matrix of the denoised images. This hurt the signal detection performance. Deeper networks made this worse, but deeper networks improved the traditional measures. Okay. And so the take-home points for this first of the case studies is that, and again, this first point, it shouldn't be a surprise to many of you. I know it's not, but for others of you, maybe it is. I don't know. But traditional and task-based image quality measures do not always positively correlate, right? If you take away one thing from the talk, that's the thing to take home, right? And this has been known for a while, but I just showed you this within the context of a deep learning example. And also the extent to which deep learning restoration methods can improve task-based measures of image quality really needs to be carefully assessed, and we need to do this in an objective way. Okay? And also, I'm not going to talk about this, but this also suggests there's just a great opportunity to incorporate task-based information into the training procedures of these networks. And I know some of you are working in this direction as well, but I think that's really an interesting process to look at. Okay, so for more information, we have a couple papers here. And Kaiyan Lee is the lead student who performed the simulations relevant to this case study. And we have a TMI paper in 2021 that describes that. And there's also a paper on a related topic of super resolution, single image super resolution, and its impact on binary signal detection that appeared in JMI last year. Okay, let me move on to the second case study. So we're going to consider a different deep learning technology now. We're going to consider a deep generative model, specifically a GAN, a generative adversarial network. And many of you, I'm sure most or all of you have heard of GANs, and many of you, or some of you may be using them, but in medical imaging, they're quite a topic of interest, I will say. They're being used for image reconstruction. For example, you can use a GAN to learn a prior and then use that to constrain a reconstruction problem. And there's been work that has extended some of the compressive sensing theory for use with GANs. GANs are used for image-to-image translation, conditional GANs in particular. And then you could also think about using GANs to describe object variability for virtual imaging trials. So related to what Paul talked about in the last talk. So instead of using XCAT, you could imagine training a GAN to describe background variability, anatomical variability, and use it for that way. Okay, so I don't have time to really talk about the nuts and bolts of GANs. So, I mean, if you don't know what they are, I'm just going to give you just a very high level interpretation. Hopefully that's good enough for this talk. But GANs are a class of implicit generative models. By implicit generative model, I mean a generative model that samples from some implicit distribution that we don't have direct access to. So if you imagine that we're looking at brain images, like I've shown here, we can imagine that a collection of brain images from a particular patient cohort are described by some high dimensional PDF that I've plotted here. And of course, we have no way of accessing that PDF. But what GANs try to do is they try to learn an empirical PDF that's associated with these training samples and then sample from that PDF. Okay, and in principle, it sounds wonderful, right? From an imaging science perspective, I mean, who wouldn't want to characterize PDFs? We can do so many things with them. But unfortunately, it's hard to get these models working in practice, and this training them is notoriously difficult. But anyway, this is what they seek to do. Okay. And here's some examples of images from a GAN that we trained in my lab using brain MRI images. The images in the red boxes are actually the GAN generated images, and the other ones are the actual real measured images. And so again, you can see the visual quality seems to be pretty good, pretty impressive. I don't know, maybe a professional radiologist could pick out the fakes, but to many of us, it would be hard to distinguish between the real images and the fakes. When I say fake, I mean the GAN generated images. Okay. But again, we're medical imaging scientists, right? So looking good is not enough for us. Okay, that's another important take-home point, right? So just like other deep learning technologies, GANs can certainly produce images that look plausible, at least to the non-expert, but are in fact incorrect. Okay, and while mere plausibility may suffice in certain computer vision applications, it's not good enough for us. Right? We don't care if an image is plausible. We need it to be either correct or we need the image to be useful for some diagnostic task, right? The other thing is we don't really understand what statistics are being captured by GANs or really by any of these deep generative models. So that's something that we need to be concerned about and look at as well. And the objective assessment of GANs is almost entirely lacking. Okay. So let me remind you about what some of the traditional valuation metrics are that people use to describe GANs. So in essence, when you try to assess a GAN, what you're trying to do is you're trying to compute a distance between the distribution of GAN-generated images and the distribution of real images. Right, you can imagine you have the GAN, you sample images, you have a collection of images, you have your training images, so you have this collection of real images. So if everything worked out well, these two distributions of images would align very closely. They'd be close to each other in some sense, right? And some popular metrics that are used to assess this closeness are given here: the inception score and the Frechette inception distance. Okay. And they both use an inception classifier to embed the images into some low dimensional space and then use some divergence metric to compare the distributions. But these are really not perfect, and everyone knows that these are not perfect. So this is not new. I'm not trying to pick on them, but just trying to remind you. Both of these traditional metrics, again, they're based on the inception network, which is pre-trained on natural images, which are unrelated to medical images. And potentially you could retrain that network on medical images if you wanted. But in any case, the inception score can easily be fooled. Here's an example from the computer vision literature from one of these papers here. A GAN was trained on these natural images on the left, and here are images that were produced by the GAN. They look terrible, but actually the inception classifier gave them a good score, right? So the inception score really we got to worry about. The FID, the Frechette inception distance score, that's a little bit more reasonable. If an image has a good FID score, then generally it looks kind of good, right? But again, there's no guarantee that the medical relevant statistics are actually captured. So to look a little bit deeper, we're going to consider a simulation study where we used GAN to learn mammographic texture. And what we did was we considered 5 different models of mammographic texture. And these are different types of clustered lumpy background models. And they differ in how the specific texture is formed. Okay? But basically, we are able to compute training data for each of these 5 CLB models. And then we trained a modern GAN for each of those models by use of that training data. Okay? And with the GAN we trained was a modern one of the style GAN. So we used a lot of electricity. We trained 5 GANs on those 5 models. Okay. And here are examples of some of the realized images. On the top, these are actual examples of the real images that were produced directly from the CLV model. On the bottom, these are images, the fake images that were produced by the GAN. And each column corresponds to a different type, one of the 5 types of CLVs. Okay, so if you take a given column and you look at the top 2 images and the bottom 2 images, visually they look similar, right? So I think I hope you agree that visually the GAN's producing images that look reasonable. If I jumbled up all the images in each column, I don't think that any of us could tell them apart. Okay. But again, the plausibility is not good enough for us. So we need to look deeper. So the first question is, how does the FID correlate at all with how well texture statistics are learned? Because these are basically texture models, right? So for each of the 5 GANs, we looked at the FID score versus training iteration for the GAN. And then we also computed the KL divergence between a collection of texture features. And we compared the 2. The second question is, are the second order statistics actually learned accurately by the GAN? And to address this, we looked at the radial average autocorrelation function. And then we also performed a binary signal detection task. And I guess now's a good time to mention that this is a collaborative work with folks from Illinois, Kelkar, Godis, Brooks, and also Rongping Zhang, Kyle Myers, and Prabat from FDA. So I appreciate their collaboration. Here's just a description of the signal detection study that we implemented, and then I'll go on to the results. So we considered a binary detection task, a signal known exactly, background no statistically task, right? And so we have our image data G can be expressed as some background image plus noise, or the background image plus a signal plus noise. So we assume the signal is known. It's just going to be, again, Gaussian blob. But the background is variable, and of course, so is the noise. The difference here is that we did two different studies. In one study, the background B corresponded to a true CLB realization, right? It's one of the real objects. In the second study, the background was corresponded to one of the GAN-generated CLB realizations. Okay, so we did two signal detection studies using the Hotelling observer, and we wanted to see if the signal detection performance was different. And if it is, that's going to tell us something about the second order statistics that were learned, because the Hotelling observer, again, uses the covariance matrix to form its decision. So here are some results. On the left, we have the FID score versus the GAN training iteration. On the right, we have the KL divergence that describes the distance between the distribution of texture features versus training iteration. Again, this is with respect to the ground truth values. And really the take home point here is that each of these curves in different colors corresponds to one of the 5 CLB models. And the rank order, if you rank ordered these curves in the left and the right figure, they're different, right? Here, the blue is on top, over here, the red. So the rank order is different. So the FID score and the KL divergence based on the texture features, it tells you different stories about which model is doing the best. And so this is cause for concern. And again, it's just a reminder that we can't rely, I'm not saying don't use FID score, I'm saying we can't rely exclusively on the FID score because it might not be tuned in to the actual statistics that we're interested in. Here are the results of the first and second order statistics. What I'm plotting here are just the radial average autocorrelation function computed using the real CLB objects and the fake, in other words, the GAN-generated CLB objects. And here the agreement is quite remarkable. So the autocorrelation structure was spot on for each of the 5 CLB models. So that's great, right? That seems to be good news. And here are the results of the signal detection study. Okay, and what we saw was that the Hotelling observer performance varied depending on how we define the training and the testing data, whether it was GAN generated or whether it was the actual real CLB images. So if I look at this table here, the training data, that describes the data that the Hotelling template was computed using. Okay, so if we look at the first column, if we compute the Hotelling template using the real CLB images, and then if we apply the Hotelling template to real images, we achieved an AUC of 0.62, right? So it's kind of low. It was a tough signal detection task, but that's fine. If we go to the second column, now if we use the GAN-generated images to compute the Hotelling template, and then we apply the Hotelling template to GAN-generated images, now the AUC drops to 0.52, right? We were hoping it would be 6.2, but no, the Hotelling observer could tell something was awry here. And similarly, if we compute the Hotelling template using the real images and then apply it to the GAN-generated images, we had an AUC of 0.55. Okay? So what this tells us is that we are not, the GAN wasn't able to fool the Hotelling observer in a sense, right? Quite simply, that's what it means. So that implies that not all of the second order image statistics were actually learned correctly by the GAN, right? Because we know the Hotelling observer uses the covariance matrix. So in terms of the summary of these results, the GAN produced images, they look plausible, they look great, right? The images look great, right? They possess correct first order statistics, they possess the correct autocorrelation structure, but when we use those GAN images in a virtual imaging study for a signal detection task, we got different signal detection performance. So that means somehow not all of the second order statistics were learned correctly. So you can see how complicated the story is getting, right? So, I mean, if you were bold to ask whether this GAN was trained well enough or is this good enough, I mean, I have no idea, right? And you should have no idea either, quite frankly, because it depends on what you're using it for, right? So this is showing you that when we use new technologies such as GANs, we really need to be careful how we assess them because it's very easy to get misled. And so finally, the take-home points, GANs and other deep generative models, I mean, they're wonderful. They're my favorite machine learning model. They hold potential for medical imaging, I believe, but traditional evaluation metrics are inadequate. The extent to which these fancy models are actually learning the statistics we care about, it's unknown. So there's an important need for objective assessments. And this is something our community can lead, right? We can't expect the other people, machine learning, pure machine learning, computer vision, we can't expect them to do that. This is our job to objectively evaluate these technologies for our tasks, right? That's what we're supposed to do. Right? Okay, so I think I might have a few minutes left, and I just want to kind of maybe just advertise some definitions for hallucinations in tomographic imaging. So I'm switching gears now. Now I'm talking a little bit more about image reconstruction. Okay, where to start here? So we all know that machine learning methods, deep learning methods are being used widely for inverse problems, including image reconstruction. And the hope is that using a deep learning method, for example, we can exploit information about prior information about the object we wish to reconstruct, and hopefully we can mitigate data incompleteness or noise more efficiently then. Okay? But the price to pay is there's no guarantee that this learned prior that we're exploiting, there's no guarantee that it's actually fully correct, and there's a possibility that false structures can be introduced into the images, right? So these false structures in the community are generally referred to as hallucinations. And hallucinations are different than other artifacts in the sense that we generally refer to hallucinations as artifacts that are introduced by an incorrect prior that the reconstruction method has used. Okay. And until recently, although the word hallucinations being thrown around all over the place, until recently, there was really no formal definitions for what hallucinations are within the context of this type of problem. For the single image super resolution problem, the word hallucination has been in the literature for probably 15 years, maybe close to 20 years. It's a well-known phenomenon. So here's an example I took from the computer vision literature of a single image super resolution work. On the left, this is a low resolution image. And then on the right, this series of images was produced by a learning-based super resolution method. Okay? And two observations. One is that all of these images are consistent with the original low resolution image. So in other words, if we applied the relevant degradation operator to these images, they would all map to the same low resolution image. That's one thing. Second thing is you can clearly see that all of these images are different, right? The textures, the high frequency structures are different, right? So in this context, they were viewing hallucinations as a win, right? Because the network is filling in these textures, these high frequency structures that weren't present in the image. But again, in the context of medical imaging, I would hesitate to call this a win. I would call it terrifying, to be honest with you, right? Because in medical imaging, again, we don't care about plausibility. We want to know, is the image reliable? Is it trustworthy? Can a doctor use it to make a life-altering decision? Okay. So anyway, motivated by this, for general image reconstruction tasks, we could look at the incorrectly estimated component of the object estimate that lies in the null space of the operator. And we could generalize this notion of hallucination to linear inverse problems in tomography. Okay, so to do this, we proposed hallucination maps. And hallucination maps, as I'm going to describe to you shortly, they can be defined in the two subspaces of the domain of a linear imaging operator in the null space and in the measurable or the informed subspace. And the work I'm going to be reporting was described in the papers last year in TMI and Saitam Bhadra, Varun Kelkar, Frank Brooks, where my colleagues are participating in this. Okay, so just some quick notation, and then I'll just give you some definitions and some examples, and then I'll be done. So consider a linear imaging system, G equals HF plus N. Let's consider we have a null space. So again, the null space is the collection of all objects in the domain of the imaging operator that map to zero. So basically the objects that are invisible to the imaging system. The measurable subspace is just the orthogonal complement of the subspace. So the objects in the measurable space, the imaging system can clearly see. And we know if we have any object that we're going to image, we can always uniquely decompose it into a subspace, a component in the measurable subspace plus a component in the null space. And what we're going to do is we're going to give definitions for the hallucinations in each of these components. Okay. So the first issue is, well, if we have an object, how can we decompose it into its null component and its measurable space component, right? And certainly this is not a simple matter, especially for large scale tomographic imaging systems. In fact, it's still an open problem topic of future work, but at least formally, we can decompose it using the Moore-Penrose pseudo inverse, and we can define projection operators, right? So the measurable component can be thought of by acting a measurable space projection operator on F, and that can be formed by taking the Moore-Penrose pseudo inverse H dagger, or a truncated version of it, which is H dagger T, if we're talking about generalized spaces, acting on H, acting on F. And similarly, for the null component, we can always pick off the null component of an object by acting a null space projection operator on F. Okay. And another definition that I'm going to need here is F hat TP. This is defined to be the image reconstructed by a truncated Moore-Penrose pseudo inverse, which is a stable linear estimate of F. So F hat TP in simple terms represents the component of the object that you can stably reconstruct from the data you were given, right? So we would hope that your reconstruction operator could recover that, because that's for free. Okay, so why do we need hallucination maps? Why can't we just use error maps? It's a fair question, right? So here's an example where we have an object and we have a reconstructed image. And if you look in the center here, there's some clear artifacts in the center of the reconstructed image. We could compute an error map, but just by taking the difference, absolute value of the difference between those two images. But the error map is filled with all types of structures, and it's really hard to tell whether this error in the middle was a hallucination or whether it was an artifact coming from some other cause, like for example, from data noise, okay? And so if we want to be unambiguous, and if we really want to identify hallucinations that are attributable to the prior, because if we really want to understand, okay, is the learned information hurting or helping me, then this might not be good enough. Okay. So let me define quickly just two hallucination maps. First is the measurable space hallucination map. And it's given it's a simple definition given here. So let F hat mes be the measurable space component of your reconstructed image. So you reconstruct an image, you pick off the measurable space component. Right? And then from that, we subtract the component of the object that we know can be stably reconstructed using, for example, that truncated Moore-Penrose pseudo inverse. If we do that, we can define this quantity F hat HM mes, and this is our measurable space hallucination map. So this map measures discrepancies in the measurable component of our reconstructed object with respect to the stable estimate in the generalized measurement space. The second definition, which is probably more interesting, has to do with the null space, right? So in this case, imagine that F hat null is the null space component of our reconstructed image. Again, so we reconstruct an image, and then we'll either iteratively or using whatever projection operator you can compute for the null space, we'll estimate the null space component. And then from the null space component of our reconstruction, we'll subtract from it the true null space component. So here, this can only be done in computer simulations, because here we're assuming we know the ground truth object so that we know the ground truth null component. Right? The ground truth null component by definition cannot be reconstructed from our incomplete data. So we have to use simulations here. But if we take the difference between the null components of the reconstruction and the true object, and if we throw away or we set to 0 the negative values, now we have what we're calling the null space hallucination map. And this is very different from a traditional error map, in that if you plotted this, then it's really just going to show you where there are errors introduced in the object that are due to the prior, right? Due to the learned prior. Yeah. So in certain applications, this could be useful. And then finally, there's one other thing that we could throw on here. These hallucination maps, sometimes they're very complicated and hard to interpret. You could imagine applying an image processing operation to these hallucination maps to make them more useful, right? So imagine that T is an image processing operation that localizes some task relevant features or textures, which I assume you know, right? You're going to have to know that. You're going to have to bring that knowledge to the table. But if you know what your task is, and if you know what object features or textures are relevant to your task, then you can imagine designing an image processing operator such that when you acted that operator on your hallucination map, you would get basically an image processed hallucination map that filters out all of the hallucinations that you don't care about and just zooms you in to the hallucinations that you might want to worry about or you might want to look at closer, right? So that's what we call a specific hallucination map. So here, just before I end, just a couple of quick examples. So what we did was, and again, here I'm comparing 3 reconstruction algorithms here. Let me be very clear. I have no interest in which one of these performs better. Certainly, all 3 of them were not optimized. My only point here is to demonstrate the use of the application of these hallucination maps. Okay. So we trained a UNet on a collection of brain images from the NYU FAST MRI data set. We also implemented a PLS-TV method and a deep image prior method. And again, the regularization parameter for the PLS-TV was just heuristically chosen. So we're not going to claim anything about optimality. Just want to demonstrate things. So here are some results. The true object is shown on the upper left here. There's a couple ROIs here in the blue and the red. Here are in each row, we show the images for the image corresponding to each reconstruction method: UNet, PLS-TV, DIP. And the first thing we notice is that these were evaluated on in-distribution testing data, at least with respect to the UNet training data, right? So if we look at the ROI in the red box, we can see the UNet actually did a remarkably good job of recovering that region of the image, where the PLS-TV is over-smoothed. Well, that's our fault. We chose the regularization parameter wrong, but that's irrelevant. Point is, this is over-smoothed, this is over-smoothed. Now, if we look at the error map, it's here, and we have the null space hallucination map here, and here are the image processed, or the specific versions of the error map and the hallucination map. So a couple of things. First of all, obviously the error maps and the hallucination maps look different. They should. They're different things. Second thing is that the hallucination map for the UNet is much weaker than the hallucination map for the other 2 methods. And again, not claiming the UNet's better. I'm just saying for these particular realizations of the algorithm, you can see there's much fewer and weaker hallucinations here. And this is consistent with the observation that many other people have made, that despite some inherent potential issues with instability, when applied on in-distribution data, a UNet learned operator can work surprisingly well. Now, if we change it, now let's look at some out of distributions. Now we applied these reconstruction methods to out of distribution data. They're very out of distribution. Actually, it's a different type of patient. Again, true object is here. The 3 reconstruction methods here. The thing we see right away now, if we look at the UNet, the story is very different. Now, if we compare this to this, the UNet obviously has some false structures in there. The UNet, as soon as we stepped out of distribution, now the UNet lost its nice behavior. The PLS-TV and DIP did much better on the out of distribution data. And these errors here, if you look at the hallucination map, you can actually see these structures in the hallucination map for the UNet. So again, this is just confirming what other people have seen, that when you have a data-driven method and you go out of distribution, the data-driven method can hallucinate, and using hallucination maps, we can start to localize, we can start to see those hallucinations. That's basically the take-home point. So I think I need to end now. So just for the summary of these hallucination maps, we formally defined hallucinations in tomographic image reconstruction from the perspective of linear operator theory. These maps can be used to identify false structures that are attributable to the reconstruction prior. Certain data-driven methods may result in structured hallucinations when there's a shift in the data distribution. And you could imagine that this opens up the door for also computing new figures of merit based on hallucination maps. So for example, you could, I'm just throwing this out there, we haven't done it, but you could imagine computing probabilities of hallucinations and then using that to compare reconstruction methods. So with that, I'd like to just thank my group and funding, and yeah, thank you very much for the invitation. Here goes trouble. Here goes trouble.
Just a couple questions. You must have thought about it. I want to play a little bit evil advocate for deep learning here.
Oh, sure.
You show that I agree with you. PSS or whatever metrics are going to give you different results than the ideal observer or linear or hoteling or whatever. I'm not surprised, because if you use another CNR defined in different ways, it will give you different things. But they are going to depend on other parameters as well. You show that in certain case, very nicely the layers as a parameter. What about the other parameters? If you play with the other parameters, so maybe room is better than your ideal observer.
Yeah. Well, I don't know about that, but yeah, certainly the point's good. There are many parameters, and you could investigate. You should investigate all of them to whatever extent is feasible. This was just an example of what happens when you vary one parameter. But yes, certainly you should do it for others.
Yeah. So this lead to my question to you. Do you think ideal observer or Hopkins observer is better that more in terms of detection text, better correlates to the human observer? Are we sure about that?
Oh, so this is completely beyond the scope of my talk. So I didn't want to talk.
So why do you use that?
So basically, yeah. I mean, if I had to guess, I would say the human observer was somewhere between the non-pre-Whitening match filter and the Hotelling, maybe somewhere in between there. But I would want to defer to an expert.
I just want to stick with it. So finally, when you talk about a hallucination, are you talking about some like observer kind of things, or they are noise, or are you talking about exactly solve that the function?
Could you repeat for which?
Part? You said that basically why trying to understand what you're saying. You write F equals F measure plus H hallucination, whatever. So that means you are actually trying to determine the function itself. It's a mathematical problem.
So
are we talking about inverting that?
You're talking about decomposing the object into components and measurable components. Yeah. So
if we can invert it, then we can invert it. If we cannot invert it, we cannot invert it.
Yeah. So for that, if I'm following you correctly, in order to compute those hallucination maps, we need to decompose the reconstructed image and maybe the ground truth object into its two components, the null space component and the measurable space component. And to do that, in principle, you can act a projection operator on there. The question is, how do you construct that projection operator?
Well, if it's a CC model, you do it. There's no error if you can solve it.
Right. So that's a good point. So here I'm assuming, I was assuming a D to D model. So I'm assuming that we have a D to D. But the issue is, how do you construct those projection operators for large scale systems where SVD is not really an option anymore?
Yeah, but that's the inverse solution to the inverse problem all about, right? We're trying to solve the whole thing, precisely, just like in CC case. But anyway, so okay, thank you.
Yeah, sure.
Thank you for your interesting talk. I was curious, in the pseudo inverse you are using, you said you were using a truncated approximation, right? So how do you decide the level of truncation? Because a large truncation involves not using smaller singular values, which are associated to high frequencies. So I was wondering, I was curious about how you decide the level of truncation to be sure that you are not losing high frequency information. And also, if you think that other regularizations, for example, Tikhonov regularization, could be performed better or not in your approach? Thank you.
Yeah, that's a great question. So the answer is, we assume that we have knowledge of the noise model, and basically the truncation parameter is chosen so that the reconstruction problem is stable in a prescribed sense, right? And I don't think you'd really want to use any other sort of regularization, because by definition we want that just to be a simple linear estimate, unregularized estimate to whatever extent we can. Yeah.
Thank you.
Hi, thank you for the great talk. I have two questions. First is, so are GANs enough for medical imaging? To answer this question, you showed several experiments to validate if GANs are enough or not. And I think those are all empirical experiments. I wonder if there are also some other approaches, like theoretical analysis or some more analytic experiments to validate if GANs are enough or not. That's my first question. Second question is are GANs enough or not? Is it more the technical question, or is it a philosophical question? Because the reason I ask is, depending on the answer, I think different approaches to validate the answer should be taken.
Okay, yeah, no, those are great questions. The answer to the first question is no. Right. So basically the assessment of GANs is a wide open topic, even in the pure machine learning field. No, I mean, this is a very active area of research, and no one really knows how to perfectly evaluate GANs. So it's very much an area of research. But one of the points I wanted to make was that as medical imaging scientists, our view on this should be probably different than the view of someone working in non-medical computer vision. In terms of the second question, it is a technical problem. I mean, maybe it is a philosophical problem, I guess, but at the bottom line, it's a practical problem, right? I mean, because if we're going to use GANs in some sort of medical imaging pipeline, then we have to have confidence that it's doing what we need it to do, right? I mean, just like any medical imaging technology, we need to rigorously evaluate it, and we need to evaluate it using objective measures of image quality. And so there's no deep learning technologies are no exception to that.
Thank you.
So a couple of questions. Firstly, you describe how you construct these hallucination maps, and then you have a processing operator to turn it into something practically useful. Do you, firstly, could you give us a bit of a taster as to what you actually did there?
Sure.
And also, do you think that processing operator introduces bias or is another source that we need to be worried about? So
yeah, let me
okay.
yeah, so that's a good question. So so those process hallucination maps, or the specific hallucination maps, as I termed them, in this particular case, for the examples I showed, we did something very simple. Basically, we wanted to apply an image processing operation that identified regions of structure, right? So if there's just random noise in the hallucination map, we don't care. We want to identify structured errors. So to do that, we histogram equalize the images. We basically convolve with a Gaussian and then threshold it, and that's all it was.
Okay. And secondly, you spend quite a lot of time addressing the challenges of GANs, but so they are particularly susceptible to hallucination issues. And what's your feeling about the relative merits of GAN type approaches versus more directly regressed networks?
Versus more what?
Directly regressed networks. So like a more typical U-net regression.
Oh, I see. I mean, it's a good question. I'm not sure I have the answer. My preference, my personal experience is that GANs are interesting, but they require further validation. Whether a GAN is better than a competing generative model, again, it's no one knows. No one's really looking at these things. Everyone's too busy downloading models and waiting for the next model to come out instead of looking at what's actually going on. So I don't know. Yeah,
okay, great.
But something interesting to look at. Yeah.
Thanks, Mark. So I want to go back to your first topic in terms of observer models. I think it's well established that traditional regularized iterative recons can improve things like detection performance on those kind of things. On the other hand, if you show those images to a typical radiologist, they don't want to look at it because it looks unnatural to them, right?
Yeah.
But what you demonstrated in your talk is you can have neural networks that produce very natural looking images that don't necessarily improve the detection task. So I was wondering if you could comment on, you just touched briefly on your AI observer model, and I was wondering if you could comment on that a little bit more, and if there's a way that can help us bridge the gap between these two competing sort of metrics of image quality in any way.
Sure. Yeah. So kind of the AI observer model I mentioned, that was basically a learning approach to estimating the ideal observer. And so the ideal observer can be used to compute the efficiency of an anthropomorphic or a human observer, right? But they're still quite different things, right? The ideal observer versus a human performance. So the ideal observer is used to set upper bounds, basically, in performance that that no one, including any human, can surpass. But yeah, so the point I really wanted to drive here, again, it's not that the denoising networks aren't useful. I mean, certainly there's people in the room who are using them for CT denoising. They're useful, right? But the point was that don't take it for granted that they're useful because the traditional metrics are good, right? So in this case, what was happening was the denoising network was producing images that look reasonable, but at the same time, they were perturbing some of the underlying statistical structure that the observer cared about. And that, that could be explained why the performance was different.
Thanks.
Hi, Dr. Anastasio. I really appreciate the talk. I actually have seen your work from TMI, and I was very glad that I could see you in person today. At the same time, when I was reading your work, I was reading about epistemic uncertainty and aleatoric uncertainty about deep neural networks. I wonder if you could comment on maybe the similarity or the difference between the hallucination map and these uncertainty estimation.
Yeah, so that's a good question. So uncertainty estimation is also a really interesting topic that's gaining a lot of traction, right? So the one fundamental difference, the uncertainty maps, they're basically computed using an ensemble of reconstructed images, right? Where these hallucination maps, this is for a given reconstructed image, we're going to decompose it and compute these maps. You could ensemble average them, but the definitions I gave pertain to a particular single reconstructed object, right? So yeah, I'm not sure in terms of some deeper connection, there very well could be. You would think that the uncertainty maps certainly should be influenced by errors in the null space, which we're defining here, right? But I haven't formally thought about any connection between them, but I think it's an interesting thing to think about.
Thank you very much.
Mhm.
Hi, thank you very much for the interesting talk. So I'm just wondering, like, if you're incorporating like any physical models or the image formation process into the network, will that improve the performance? Like, maybe like, for example, the noise model of the image or like the image formation process physics, if we incorporate that into network, kind of improve the performance.
Yeah, sure. I mean, I'm kind of old school in my thinking. I'm a professor of Xiaotran, so I mean, I would say incorporate what you know, right? I'm not an advocate of learning something that you know, right? So if you know, if you know the physics, if you know the noise model, I would expect incorporating that should help. But again, I think you'd have to assess that, right? So, but I think again, how that's relevant to this talk is that you'd want to assess that using objective measures and show what type of improvement you got by incorporating certain factors into your forward or your reconstruction model.
Thank you very much.
Mm-hmm.
Hello, thanks for the great talk. About the hallucination maps, I see how they apply when the forward model has a null space, like the example with the woman's shirt.
Yeah.
Can they also apply to situations where the forward model doesn't have a null space per se, but there's noise? So like in CT, if you had fully sampled CT, you may have like the Fisher information matrix with eigenvalues approaching zero, but never actually reaching zero.
Yeah, that's a great question. And the answer is yes. And actually, that's what the measurable, it would be the measurable space H map. So basically, you take this formulation, and as soon as your null space goes away, your null space hallucination map is no longer relevant, but that measurable space hallucination map is still very relevant, and that would apply in the situation that you just mentioned.
Great, thank you very much.
Mm-hmm.
Well, thank you, Mark. That was fantastic. One more round of applause.